All right, so I wanted to go ahead and step back for a second. I noticed in my last video that I made a little mistake when I was calculating my total acceleration. I was doing it a little too fast. And total acceleration, if we go back, is going to be a vector. Okay, so when we're looking at total acceleration and we're just looking for the value, it's going to be the centripetal acceleration squared plus the tangential acceleration squared, square rooted. Okay, so this is what we are looking for in this problem. Okay, so let's go ahead and correct that. Okay, so our acceleration is going to be 1.5 squared plus 3.125 squared in a square root. So if we put that into our calculator, we get our acceleration is 3.47 approximately meters per second squared. Okay. Oops. So that is going to be our total acceleration of the particle. All right, so now we can move on. I was talking about relative motion in one dimension. And I want to just kind of repeat what I was stating here. So for an example of relative velocity, if we have a person sitting on a train, okay, so we've got a person on a train, okay, and the train is moving east, and then the person gets up and starts moving west, okay. The velocity relative to the train, so the person's velocity relative to the train is going to be in the negative direction of the train movement. Okay, so if I say that this is the positive x direction, okay, the train is moving in the positive direction relative to the earth, okay, and the person is moving in the negative direction relative to the train. So to figure out the velocity of the person relative to the earth, we do this in such a way. Okay, so that velocity will equal the velocity of the person relative to the train plus the velocity of the train relative to the earth. Okay. So just note how the transcripts are noted. Okay. So the order of the subscripts, the subscripts, sorry about that. This is kind of a visual representation of what we're looking at. Okay, so if we have the train moving 10 meters per second in the positive x direction, and the velocity of the person with respect to the train is in the negative x direction, okay, we can find the velocity of the person with respect to the earth by adding these two together, okay. So we can look at this in 2 dimensions as well, or in 3 dimensions. Okay, so if we consider a particle P and reference frames S and S prime. Okay, so just like in here, we have 2 reference frames. We have S, which is this first one with X, Y, and Z. Then we have a second reference frame, S prime, with X prime, Y prime, and Z prime. Okay, and we have 1 point, P. The position of the origin S prime as measured in S, okay, so the position of the origin of S prime here as measured in S is R S prime S, okay, so that's this vector here. The position of P as measured in S prime is R sub P S prime. Okay, so that's this vector here. And the position of P as measured in the S reference frame is r sub ps. Okay, so if we want to describe all of this motion, our position, velocity, and acceleration in either frame, we can use these equations. Okay. Note if the velocity s prime relative to s is a constant. So if the velocity of s prime relative to s is a constant, then a s prime s equals 0. Okay, so this value here would equal 0. So if this guy here is equal to a constant, that's what it's stating. Okay, and we can extend this to any number of reference frames, so it doesn't just have to be 2, it could be 3 or however many reference frames. So this is an example of that for a particle with these velocities in frames A, B, and C. We can write these velocities. Okay. All right, so let's go ahead and do an example. So this states a truck is traveling south at some speed, 70 kilometers per hour, toward an intersection. A car is traveling east towards the intersection at a speed of 80 kilometers per hour. What is the velocity of the car relative to the truck? Okay, so we want to know velocity of the car relative to the truck. Okay. Remember we just learned that velocity of 2 different reference frames will be those 2 reference frames then added. Whoops, that's supposed to be a V, not a C. Okay. So V, T, E. Okay. So this is what we are trying to find. Okay. So, oops. We want to find this here. And they're in different directions. So I would say we have the car 80 kilometers per hour in the i-hat direction plus, the truck traveling in the south direction. So I'm going to put a negative here if this is my coordinate system. Okay. And that'll be j hat. Okay. So this is going to describe my velocity. Now if I want my velocity of the car as a magnitude, I will take these 2 and square them, and add them, and take the square root, just like our other vector problems. Okay, so I can put that into my calculator. 80 squared plus 70 squared, square rooted, and I get 106 or I guess I can just leave that off, kilometers per hour. So the magnitude of the velocity of the car relative to the truck is 106 kilometers per hour. We can also find the direction of the velocity, so we're going to go ahead and do that real quick. So tan inverse of the y component, which is negative 70, over 80, the x component. So tan inverse negative 70 over 80 is negative 71.8 degrees. Actually, let me make sure that I have it in the right. Nope. Didn't have it in the right units. So we have negative 41.2 degrees. Okay? So that is the direction of the velocity vector. Okay, so notice that I had the negative put in here. Okay? Now we want to make sure that this is correct. So if I go back and I look at the equation that I first began with, notice the symbols I have on here. So V sub CE plus V sub TE. Remember, in this subscripts here, or in this equation here, the subscripts have the same inner subscripts. Okay, the subscripts and the inner sides are the same, and the outer, they're different. So I should have the Earth on these two. So let me go back, and I do not. So this is a little bit tricky, okay, in remembering. So this should be V sub CE bar minus V sub ET bar. Okay, so we have to insert that negative in order to move the subscripts around. Okay, so now this should be positive, this should be positive, and this should be positive. And that makes this value positive as well. Okay, so my magnitude stays the same, but my direction does change. Okay, so be careful when you're going through these problems. Okay, watch out for things like that. Okay, so our velocity of the car relative to the truck then is somewhere in this direction. Okay, because it's about 41 degrees. Okay, with the velocity of 106 kilometers per hour. All right, so with that last example, that'll be it for this lecture, and we'll see you next time.